So before we go in, let's look at the jewels of APOD. Remember, since the 25 years, every day got one picture. That means there are more than 9,000 pictures. So there are two American professors in America. They choose the best picture to load every day. So what kind of picture they come from anywhere, right? You can never expect what will come every day. Very exciting. So these are the jewels. So this is my
Let's
selection.
look at the jewels of APOD. Remember, since the 25 years, every day got one picture.
But anyway, okay. Now, so so every so there are many of them, but very nice. So this is my selection, But before we go there, let us go back to. Wait a minute.
Dr. Chong, at the bottom there, can you click the height, the bar below?
Height, yeah, height. I click height now. Now I want to go back to my browser. Wait. Can I go to my browser? How? Not very nice. This okay. Okay, go to the browser. Yes. Wait a minute. Okay. So this is our browser. So the one I want to go, you can see quite well, 20 this thing, Michael. Okay, we go to 22nd July. Oh yo, I really like. This is the best picture of NEOWISE so far I've seen, according to me. All right. So I'm going to click on it. I'm clicking on it now, but there's no response. Why? Now what I'll do is maybe I'll refresh the page. I'll refresh the page again and click on it. Just wait, patience. Refresh it, but it doesn't refresh. Okay, refresh. That's it. Then just look at this. Woo-hoo. So now I will scale down. So basically, it's taken by an amateur astrophotographer from Beijing, Zichuan Lin. All right, and this is taken from, you see, the Gobi Desert. All right, why Gobi Desert? Very dark sky. All right, so basically he took it, and the important thing is that it's very exciting. All right, so let's look at this thing again. I reduce it. Some people are not aware why the comet have two tails or sometimes even three tails. You look at it again. Of course, you have here the blue straight tail, ion tail, ION, ion tail, and these are the charged particles. And then you like a fan, the dust tail. So this is where he took it. And of course, basically you ask me in which direction is the comet moving. So since now the comet is going away from the inner solar system, further away from the Earth towards Mars and so on. So this, some people say, okay, the comet is going down. Wrong. The comet is going down. Wrong. The comet is the nucleus of the comet is actually going here, going in this direction. All right. So this the direction is traveling, and because of that, in the fourth direction you see the ion tail, and this is a lagging tail, the dust tail. So some people say, how do you form these two tail? Because this ion tail is blue color because you have fluorescence. I explain in detail later fluorescence, and this is a dust tail. So this light here is given by the excitation of the electrons in the ions, ION. Remember, in the comet, there are all types of what they call particles, ice particle, and so on. So the solar energy, right, which is the solar wind, will hit this coma, the nucleus, and also the sun's heat will evaporate it out. And when you evaporate out the solar, you know how fast is the solar wind, what is solar wind? The electrons and the protons and the charged ion coming out from the solar corona. So what is the speed? Listen carefully. 400 kilometers per second. So 1 kilometer per second is the speed of the bullet, fired from a gun, 400 times faster than the bullet. So all these solar particles, which are the electrons and ions, they'll hit these particles from the nucleus evaporated, and they also become ionized. So they will form here. And remember, when they ionize means what? The electron energy level will change. So now I go back to PowerPoint. So basically, the blue tail is an ion tail. So the solar wind particle that hit the the particles from the nucleus of the comet that form the ion tail are also moving very fast. So the blue tail is very fast, close to 400 kilometers per second, and they have fluorescence. So what is fluorescence? Fluorescence basically is in those ions in the ion tail. You have, let's say, you absorb a photon, all right? You absorb a photon, and these photons are what? The sunlight. It will excite the electron from a lower energy level around the ion to a higher level. Michael, you can see all this, huh? Michael, can you hear? Okay. So then later on, the electron will drop to this side, and it will de-excite lower to the ground state. But you see, the absorption difference in energy is more than the fluorescence. So when it fluoresces out, it will give off, let's say, blue light. Blue light, all right? And that is for a simple type of ion. For more complicated ion, it may look like that. So it absorbs a light here, and then will come down, and the light is absorbed from the sun is what? UV light, which we cannot see. So when it de-excite, it comes up, it is visible light, blue. All right. So that's why you see it. Michael, can you see all this? So in other words, this one, it will de-excite from UV light, you absorb. So when it de-excite, it gives off the blue light. All right. And remember what is in this the ion tail, the blue tail. Ions, ION, is actually a fast moving plasma, 400 kilometers per second. And this plasma is what? Charged particle. So any charged particle is moving will be affected by what? Magnetic field. So if you look carefully, this tail is not very straight, no? So it's affected by remember, the sun gives off a kind of magnetic field, not very strong, but even at the distance of this comet from the sun's magnetic field is there, although it's very big, but because the iron particles are very, very light, so they are influenced by the sun's magnetic field. That's the first tail, ion tail. What about the dust tail? So I repeat, the ion tail are very fast moving ions, all right, and they experience fluorescence, all right, and so by giving fluorescence, the change in the electronic energy level will give off the blue light. But this is different. This is just plain scattering of light. Just like you go out of the building, you see sunlight hit the wall of a house, and the sunlight is reflected off on the wall of the house. So this is white, all right. And remember, what is in this dust tail is actually the dust particle. So basically, it's like this. So the sunlight will come and evaporate it, and then the ions in the sunlight will hit on this, it will ionize to form the ion tail. But some of the sunlight will evaporate the dust, and the dust come here, and basically the dust is what? Neutral particle. So basically, each of these dust particle is many, many times bigger than an ion in the ion tail. So the dust here very big. And why is it have a fan shape? It means that there's a spread of the velocity. So the dust particles are moving faster because it's a lighter one. And here the dust particles are heavier dust particle, so it's a lag, because remember the comet is moving here, so it lag. So this fan is actually a spread of the velocity of the dust particle in the dust tail. So these are faster moving dust particle, slower moving dust particle. So there's another name for this, What is this? White sunlight hitting on the white dust, scattered back white light. It's called what? Our Mie scattering. Not Maggie Mee, M-E-E, it's M-I-E. So now you look at it, all right? So the white tail is actually moving much slower than the ion tail, and it's Mie scattering, all right? Mie scattering means the wavelength of the light, okay? We go back to the thing. So Mie scattering means the wavelength of the sunlight hitting the particles here, the wavelength is shorter than the particle size. So white light falls on it, white light is scattered back. So this is called Mie scattering, right? So because of the Mie scattering, and because there's a split in the particle size, you see a fan there, right? So what will happen to all these particles? So these particles, as you blown up, will actually follow the orbit of this comet and so on. So remember, what is the period of Comet NEOWISE? The period will be about close to 11,000 years. All right, 11,000 years. Now, another thing many people will ask, Can you hear me, Michael? So far, Michael. So NEOWISE, of course Comet NEOWISE got a name. So what is our NEOWISE there? It's our near Earth object. All right, I repeat, near Earth object wide field infrared survey explorer. So it's actually a telescope sent by NASA what in space. So what is it? To look for object, near Earth object. Near Earth objects mean maybe like those asteroids that can hit the Earth. All right, like the asteroid that hit the Earth and destroyed the dinosaurs 65 million years ago. So in space there is a telescope sent by NASA to study the near Earth object, and it's a wide field.
John, I can hear you.
Can you hear me now? Lai Hok can, huh? Okay, can you hear? Okay, so this is a wide field infrared survey explorer, and then there's a naming convention. Why is it like that? Can you hear me, Lai Hok, huh? Okay, so it's like that. So C means it's a long period comet, a long period, or even it's like a non-periodic comet. It's a periodic comet like a what they call Halley, 76 years. It's called P, but this is C, means a long period. The period is actually 11,000 years, and it was discovered in the year 2020. And F3, what's F3? So the naming convention like that. If it's actually A means the first 15 days of January. If B means the second 15 days of January. So A, B, C, D, E, F, 6. That means this is F means that it is found in the second 15 days of March. And 3 means what? The third comet found. So C means long period comet found in the year 2020 in the second half of February this year, and it is the third comet found in the second half of February. That's what I mean by the naming convention. So if you don't put NEOWISE in the research paper, they don't put NEOWISE, they put C2020 F30. That is NEOWISE. They don't put NEOWISE, they just put the code only. All right. So this is a naming convention, right? So now we go back to our other, all right, jewels or airport. Now can hear? Michael can hear? Okay, so this is our jewels airport. So before we go to the July airport pictures, which is basically half of it is what? NEOWISE, Comet NEOWISE. So I'll spend a bit more time on this is my selection. The past few years, to me, these are the best pictures of airport in the past few years. Okay, so it's not means ruby and diamond, it's those pictures, fantastic pictures. So we go to the first one, we go back. Okay, which is the first one? Part 1. This is in the coming airport session. Every month I have part 2, part 3. So I picked 8 pictures in the past few years, which I put in my treasure box. The jewels. 1st July 2020. I really like this. This is great. This guy from, I think from Poland. He did
Yes,
it.
I can hear you. We can hear
Yeah. He did it in Namibia, in South Africa. I tell you, when I saw it, I nearly fell down from my chair. No. So let's go to 1st of July. Okay. I will make the font bigger first. You see first. Okay. It's actually a video. Video. On the right is Milky Way. On the left is the Earth. But you see, I make the font bigger so you can read first. Then I go to the video. So basically, it's taken from where? Our rotating Earth by a Polish amateur astronomer who went to Namibia. So basically, it's actually seen. You can see the rotating sky. All right. In Namibia and so on, you can see the Milky Way and the large and so magical. But what I'm saying is, I've never seen people doing like this before. Can you imagine? I thought people do fantastic astrophotography, have exhausted all technique. No, this is another new technique. Okay, so now everyone enjoy this picture. I'll play it a few times and explain. Okay, so this is it. Okay, a bit bigger and play the video. Okay, I'm going to play the video. Don't close your eyes. Wow, 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 yeah. It will repeat twice and then I explain again. Okay, what do you mean? So what is this? This one I've never seen people do before. So basically, we have seen time lapse, isn't it? Time lapse when you put a camera on the ground in this Langkawi, and you see the Milky Way come up in the east and set in the southeast and set in the come up in the southwest and rise set in the southeast. But this different. This guy from Poland went to Namibia. It's a big country just north of South Africa, and he point his camera in one direction only, doesn't move, and his camera rotate. His camera rotate in such a way that the pattern of the stars, daytime or nighttime, going into his camera does not change at all. So the stars are not moving. Only the Earth is moving. So usually when you do time lapse, what you do? You put your camera on the stand on the Earth. So your camera is on the Earth, on the rotating Earth. But this is different. His camera is actually fixed to the sky. So his camera look at the sky, does not move. So the Earth will rotate. So he have to counter rotate. So if Earth is rotating in one direction, clockwise, the camera rotating counterclockwise, so that the sky does not change. So this is a repeating. Just look. Then, then, then. I tell you, it was so imaginative. So nice. Really nice. This is the Milky Way. So in other words, to get this one cycle, he need to have one whole day. All right, and you see at night, you see that? All the lights on the ground. So the camera that is rotating. This is great. So what I'm saying is that it's a great idea. I think some of our members, maybe you can ask our CK, Chung Kiat, to try this thing. Right? So, but he must make sure that the weather is good and point in the sky, and the camera rotate one rotation 360 degrees in 24 hours. So is the sky does not rotate, it's the Earth that is rotating. This is really ingenious, I really find this fantastic. All right. So now we go to the second APOD. Jewels, 24th February 2018. Okay, 24th February, sorry. February 2018. Sorry, go down. I hope you all can see it's a bit small. I make it bigger. Okay, 24th February 2018. I really like this one. Oh, yo, look at that. Okay, I'll show you the text, then I'll show you the picture. NGC 6946. It's taken by the Japanese telescope Subaru. Remember in Hawaii, next to Mauna Kea, on Mauna Kea, you have the two Keck telescope, and next to Keck telescope, you have Subaru. The Japanese are very proud, that their Subaru is next to number 1 and number 2, Keck 1 and Keck 2. All right, but it's processed by an amateur astrophotographer, Robert Gangler, from America, but taken by Subaru, and of course Subaru, this is Subaru. All right, so this is on the tall extinct volcano in Hawaii, 8.2 meter single mirror telescope, and it's above the clouds. And on the right will be Keck number 1, Keck number 2. So with this telescope, he got they got the picture, and Robert Gandler processed it. And of course, there are a lot of things you can see here. All right. So now we go to a smaller scale to see it. There you are. All right. You look jewels, very nice. So a lot of things you can explain about what galactic astrophysics. So this is a spiral galaxy, and you have the old star, the population. I think this is population 2 star, which are the older star, the yellow star, and the younger star is a population 1 star. All right, population 2, population 1, and where you have the blue and the red and the pink are the younger star. The yellow is in the bulge, or in the globular cluster, or in the halo, are the population 2, are the old stars. So you can see very nice. What I like is, wow, to me if some people say, well, look like a Christmas tree, very nice, all right. So I really like this picture. All right, taken by Subaru. All right, and but processed by Robert Gandler, a well-known American. He's actually a physician, a type of a medical doctor, but his hobby is what? Astrophotography. All right. We go to the second jewel. 25th January 2018. Again, 2018, 25th January. Sorry. There you are, 25th January. Okay. We look at the text first. Then we go. I think this you have seen. This one actually was taken. The first time was taken in the 1990s by Hubble, but later on they took another time. Okay. So let's look at the text first. Of course, ESA and NASA, basically this is taken by Hubble. And then you see this is our famous cartwheel galaxy. All right. This is cartwheel, something like a big wheel. This on the right, or some they call it the Ferris wheel. The Ferris wheel galaxy. All right. And then, of course, this is taken by, just a minute. Wait. All right. It is 150,000 light years away. All right. They didn't say which constellation. I can check later. So basically, what this is, of course, what Kemalangan galaxy accident. This is a cosmic accident. What a galaxy on the right, this funny looking galaxy has been damaged by this smaller galaxy. Remember, Hubble have taken a lot of what they call two galaxies that they are interacting because of what? The gravity right? So they are interacting before collision or during collision. But this is a case of galactic accident, galactic interaction after collision. So earlier, this big, I make it smaller again. So earlier, this round object is a galaxy was on the left, and these two is another galaxy is on the right. So this galaxy A was on the left, galaxy B on the right. So what happened is galaxy A moved to the right, galaxy B moved to the left. So the galaxy B penetrate through galaxy A. So in other words, there's a collision. And what happened is during the collision, there's this is actually a gravitational shock wave. So of course it's impossible to have the stars in this galaxy could hit exactly the stars in this galaxy. Remember, the interstellar space inside a galaxy is very big. Impossible to have the stars colliding with each other. But the stars in the galaxy B will interpenetrate the stars in galaxy A. So basically, the stars will pass through each other, but the cumulative gravitational pull of both galaxies interact, and they cause the shock wave. So basically, previously, this galaxy was not naked. Sorry, allow me to use the word. This is like a small spiral galaxy. Got a bulge and got spiral arm. But after collision, some of the stars in this galaxy around here was stolen by this galaxy. So some of the stars here was actually previously from the galaxy on the left. So stolen, and this part of the star originally belong here now become distorted. But this one, see, wow, look like a bicycle tire with all the spokes So basically, it's like the shock wave that will expand. But don't expect wow, the shock wave to what you call start here and reach here in 1 minute, 1 hour. No, remember our Milky Way is 100,000 light years. So this is the radius could be 50,000 light years. So it takes a long time for it to happen. So this is a case of a shock galaxy, right? So after the interpenetration of two galaxies, this become distorted and this become naked, lost many of the stars. All right. So if there are any alien civilization in galaxy A or B, sorry lah, they all be destroyed, because it's not just the stars hit each other. The whole galaxies have been completely torn to bits. It's called tidal distortion. All right. So this is it. So very beautiful. I really like it. All right. This is our cartwheel of fortune. All right. Two galaxies after collision. Now, what is the third jewel? 4th October 2017. 4th October. Okay. I really like this. Wow, yo. All right. Let's look at the text first. Okay. Of course, it's taken by ESA and so on. This is by our Herschel Space Telescope in space. So Herschel is of course William Herschel, the famous astronomer from England. Okay, Herschel Space Observatory in infrared. Now this William Herschel is a famous German astronomer that migrated to England. This famous guy. So in English astronomy, these two are famous. William Herschel, the father, and John Herschel, the son. All right. So they are the one who were amateur astronomer, went to England and became famous in England in astronomy research. All right. So this Herschel Observatory in space, NASA telescope, and they got this picture. Just look at it. So basically, it's very nice. All right. So next to the Heart Nebula, and then you look at it. So they call it the Soul Nebula in infrared. Well, it doesn't mean that it's green, blue, It doesn't mean that this is red, This is a false color imaging. They took an infrared and changed the wavelength. Maybe this wavelength here will be longer than this one. So that both are infrared. So they change it to be like red and green here. But actually, it's infrared. But it look very nice. All right. So I don't know whether you all can see the soul, soul of a person, but they call it the soul nebula. Right, very nice, very like this. You see, so that means you see all these small features here, which are many light years. You can research it. But what attract me is it really look like a soul of a human being. What do you think? I hope no comment. Very nice. So this is also next to another famous one called the IC 1805, the Heart Nebula. So the Soul Nebula, like this, is next to the Heart Nebula, right? So this is one of my APOD jewels, all right? This is my choice. I don't know whether you agree, but this is my choice. Which is the next jewel? 18 September 2017. 18 September 2017. There are 8 of them. No, sorry. Just a moment. 18 September 2018. 2017. Slowly. Wow. So nice. I like it. All right. Of course, wait a minute. I'll show you the name of the person first. Then I will explain the picture. By one American astronomer, although his name is Russian, but I think he's American. What they call astronomer, and also part of Tuan. Tuan is the world at night. So this is taken on Easter Island. All right. So Easter Island is a group of islands in the eastern South Pacific to the west of Chile. All right. It's actually far away from no man's land. And then in the Easter Island, you have found here ancient civilization. You have many of these tall statues. The civilization has died out, but they know there are some previous civilization there. But what interesting is you see the night sky from there. So nice. What's so nice, right? The 3 stars in the belt of Orion, Betelgeuse, what they call Bellatrix, Rigel, Saiph, all right? And you see Sirius there, and you see this statue there, all right? This is about the ancient Moai civilization, right? So this is our what they call astrophotography in Easter Island. And these are what? These are the clouds in the Earth's atmosphere. But these are the stars in the Milky Way, much further away. So very nice, Easter Island, all right? So another selection of the jewel of mine, which is on 1st September 2015. Okay. September 2015. Okay. Now we will make it bigger first. We make it bigger, then you can see first. Wait. Okay. So it is on our 1st September 2015. Right? So you may have a wondering what is this one? Huh? So do you expect APOD pictures always galaxy, nebula, star, planet? No. This is an experiment in the South Pole. All right. So here is there's a University of Wisconsin in America. Many years they started the Ice Cube collaboration. So basically, what they have here is that it's actually a gigantic neutrino observatory. All right. So what is this? I repeat. Okay. So at the South Pole, you have the Amundsen Scott what you call center there in the South Pole. This is the center there. So they drill into the ice and they put inside here a lot of what? Photo multiplier tube. So the photo multiplier doesn't look like that lah, but it's just to show that it's the size. So there are many of them vertically down. So basically down in the ice is about 1 cubic meter of frozen ice. So what happened is, remember, they have this neutrino detector in Japan many years ago. Remember, they have detected the neutrino oscillation Super Kamiokande. What they call a mountain in Japan. They dig up the cave in the mountain and they put in water, liquid water. But this case is they use frozen ice. So basically, from the sky, you have a from the outer space, you have the neutrino come either from the sun or from the Milky Way. They will come from top, they'll come down, and the neutrino will go and hit some of the particle, all right, and the particle will give off flashes of light. And from the properties of the flashes of light, they can detect the neutrino. So this is the Ice Cube exploration, University of Wisconsin, all right, in the South Pole. So this is our Ice Cube experiment. So do not think that your telescope might look like a tube to look at the sky or the reflector. So this telescope is what? Just put all 1 kilometer deep into the ice, frozen ice, all the photo multiplier tube. So what is the photo multiplier tube? Is you have a light, a photon coming in, a particle of light coming, a photon here. It can multiply the photon trillions of times. So it detects even a single photon it can detect. So there's one photo multiplier tube here. Second one here, many photo multiplier and many all vertically down. So by maybe let's say if there's a neutrino come here, hit here, and there's a photon given off that travel in this direction. So all around here, they can detect the photon coming here. So they work better. The photon originate from this direction. So if another one come here, the photon coming here, this detected. So they work backwards. It go there. So they can also know the direction of from which direction the neutrino is coming in, and the neutrino is mostly from the sun and from outside our solar system. All right. So this is one. Can you hear me, Lahok? Can Okay. Next one.
Can, no problem.
Can 28th of June 2015. I tell you actually, if you allow me, I remember since 1996, 1 year after Apple started, I've been trying to collect my jewels, But this one were also nice. Maybe I need to collect some jewels from the earlier days. This is from the recent one. 20th of June 2015. Another jewel. Okay. (2015), 20th of June. Wait. Of course, this is nothing new to some of you, like Michael, but to me, it's must show. All right, I like it. Why? This is the spectrum of the sun. All right. So I make the text bigger so you can see all colors of the sun. All right. So this is taken by National Nigel Sharp. It's a researcher in National Science Foundation, and all these are the famous So these are all the observatories. The big observatory they took it, and it's actually from our what they call, I think, from our Magnet Pierce Solar Observatory. Remember, if you go to Arizona, I think Chun Kiat had been there. Wow, look at this. Wow. in not very far from Tucson, Arizona, in the mountain, they built a huge series of observatory. One of them is a solar observatory called the Pierce McMahon Solar Observatory, and this solar observatory, you can see a 1 meter diameter of the sun on a horizontal surface with all the sunspot very the detail with it. And at the same time, they split the sunlight into the very detailed Fraunhofer spectrum. So with this telescope in Kitt Peak in Arizona, they get this. So basically like this, the correct thing is you don't see like that, because if this is like infrared, long wavelength to slightly shorter, and this is nearly slightly shorter. So from red to here to blue, short wavelength. But if they want to stack it out, it's very long, you know. I repeat, this is one segment. You join with this another segment, so you can join up. I remember you can see in some of the textbook in the 1980s in the astronomy textbook in USM, when you stack up from here, from the close to the near infrared to the blue, the whole Fraunhofer spectrum of the sun is 50 meters long, 50 meters long, half the length of a football field. No joke. But because of no space, so they stack it. So basically, this part, wavelength longer, this shorter, this, and why all the dark line? Of course, those are the absorption lines. Remember, our sun's photosphere and corona got elements, and the light from the surface of the photosphere pass through the elements in the photosphere in the corona, and they absorb. So these are absorption lines. So every absorption line can be explained. So remember, they quote in the textbook, no, how many absorption line in the Fraunhofer spectrum of the sun? Answer, 25,000. In fact, we have done experiment in the ground that every single element got a few thousand lines, you know. Even hydrogen also got many lines. Hydrogen is so simple. One proton, one electron also got many lines. What about calcium? What about uranium? A lot. So it's all combined together. All the elements will give this. So there are tens of thousands of absorption lines of the sun. So this is all colors of the sun, including the dark absorption line. So the dark absorption line, to put it more actually, should be all colors of the sun plus no colors of the sun. No colors, dark absorption line. So altogether is Fraunhofer spectrum. So remember, in the 19th century, there's a German scientist called Fraunhofer. He discovered the absorption line. He passed the sunlight through a prism, a glass medium, and he saw it. All right. And who are the people who work in the same group? Bunsen. Remember your high school Bunsen burner? So Bunsen will light up the gas, and Bunsen will throw over the flame of the Bunsen burner sodium. Hey, the flash, the light from the salt, sodium chloride, over the flame of the Bunsen burner is orange color, sodium. So, but throwing a lot of those elements of salt into the flame, they saw a lot of color. These are the elements. But later on, Fraunhofer analyzed all this. Wow, this is our Fraunhofer spectrum of the sun, colors of the sun. Let's look at the next jewel. 12 May 2015. Okay. We'll go to the list for July later. Okay. Say again. 12 May 2015. 12 May. Very nice. Okay, this is very nice. So this is taken by our NASA. Okay, it's processed by amateur astronomer Demi Bui. Right. So basically, this is very easy to understand. This is actually sunset on the Earth, sunset on Mars. This is the case. So already many years ago, when the remember many years ago, the Americans have landed Mariner 4. No, I think in the 1970, the first American lander on Mars. Later on, the first American rover Sojourner, 1997 on Mars. They already see that. Hey, why? This is sunset on Mars, blue sky, and you look carefully. On Mars, the sun looks smaller. On Earth, the sun looks bigger. But on Mars, sunset, you have blue sky. On the Earth, sunset is red sky, opposite from the Earth. All right. So that's it. So we always say that on Mars, very interesting, you know. On the Earth, red sunset, red sunrise. On Mars, blue sunset, blue sunrise. And it's not shown here, but they also NASA explained that on the Earth, you look up to the sky, our Earth sky is what? Blue. But on Mars, you look particularly up close to the sun, the sky is red. Opposite. So on the Earth, sunset, sunrise, red, but the daytime sky is blue. But on Mars, sunset, sunrise is red, but the sky is not the blue, but the overhead, the sky is red. Like this. So all because of the dust in the Martian sky. For example, on the Earth, why you have red sunrise, red sunset? Because of Rayleigh scattering, right? The sunlight, as it passes through more and more of the air in the Earth's atmosphere, the oxygen and nitrogen molecule we have Rayleigh scattering, and scatter out the blue. The blue is being scattered out. So what passes through thicker and thicker atmosphere become richer and richer in red. So this is Rayleigh scattering. But here is because of the dust. It's the dust that scatter out more of the blue. All right. So that's it. So this is very interesting. This is the proof why it's different. Huh? So very different. So when the China Tianwen-1 lander land there, and then this what they call Perseverance lander will land also in February next year in March. The moment in March, the moment you see something different, you see a black one. If let's say they show that the sunset on Mars is red, you know it's Tipu. The sunset on Mars must be blue. All right, the sky must be blue there. All right. So now we go to the next jewel. This is my selection. So I think that's about all from here. All right. So we have gone through this. Now we go to the rest for July this year. All right. We go bigger. So if you all see, Lighthawk and Michael, I think half of them are NEOWISE. Half of them are NEOWISE. So I will pick some of the NEOWISE. We go to today's one. Tianwen, 不是天文啊，Tianwen, heavenly question. So they launched on the 23rd, 2 days ago. We covered it with our chat group. So our Long March 5 launched from Wenchang Satellite Launch Center in the northeast part of Hainan Island. This rocket, and it's successfully inserted from the top here the Tianwen-1 Mars orbiter, Mars lander, and Mars rover. So now they're on the way to Mars. And like we discussed that day, on the way doesn't mean that all the time, the 7-month journey, the rocket at the back of the orbiter will firing. No, it's just silently going towards Mars. It's once you insert from Earth to go to Mars, the 99% of the journey is quiet. The whole spacecraft, no vibration, quiet, as if you are in a vacuum, no sound. It's just actually free falling towards Mars, right? Because you see, our Earth's velocity, orbital velocity around the sun is 30 kilometers per second, right? And then the what you call Mars orbital velocity around the sun is 24. And to leave the Earth's gravity, you must have 11 kilometers per second. So in other words, when Tianwen left the Earth, it was traveling at 30 plus 11, 41 kilometers per second. So it must slow down for 7 months until it can match the speed and direction of Mars, which is 24 kilometers per second. Then only it can orbit into around Mars, right? So now on the way to Mars successfully, but a lot of things to happen, For example, it must enter into orbit successfully around Mars in February next year, and then it must land the lander on Mars successfully in April next year, and from the lander, the Tianwen-1 rover must come out successfully, and so on. So a lot of things that can happen. We'll cover it, all right? But we know very soon, on the 30th, 1 week from now, Perseverance is going to be launched. That will be another big one because Perseverance is 4 times bigger than Tianwen-1 rover. All right. So we go to the next one. This one is another one. Of course, I like this one. 23rd of July. Look carefully. All right. Okay. This is taken by our Stéphane Guizard, French amateur photographer from the world at night. All right. This is our Castle Neuschwanstein in the Babylonian Alps. Remember, if you see our Disneyland movie, many of them like our what they call Alice in Wonderland, a lot of those castle is actually copied from this what they call castle in Bavaria. Bavaria is somewhere near Munich, right? The football club there. And you see here what? NEOWISE and a Perseid meteor shower. Wow, most likely it's the Perseid. So this is like as if this is like Fantasyland. Very nice. I like it. right? This is our fairy tale NEOWISE. This is a fairy tale. This is a very popular tourist destination in Bavaria, in Germany, So many of the Marshallese, the Americans, Europeans, they like to visit this place. It's a small castle, but look like a fairy tale, right? Big Comet NEOWISE. Another one will be, okay, let me look at this. Magic NEOWISE, all right? This is taken by one Austrian amateur astronomer, all right? So I'll explain here. Here you have on the island called Los Muchachos. Is on the Canary Islands, north of Africa, but these Canary Islands belong to Spain. And on top of the mountain, remember, you have some of the big optical telescope there, but you have a cosmic ray telescope. So this one, the diameter is 17 meters with many, many segments. What are the segments? Polished aluminium. They polish so much that look at mirror. Hey, you can see the Milky Way reflected of the mirror here, right? And this is a Comet NEOWISE, another similar. So these are twin. There are three of them here. Telescope. So basically, what do they do? All right. So this telescope is an old technology, and some people say, I don't know got this type of telescope. Then I'll tell you, I show you lah. Got this type of telescope. All right. So basically, they're studying the famous Cherenkov, what they call radiation from the sky. So it's like this. Let's say somewhere in the few thousand light years from the Earth, they actually study the gamma ray. There is a pulsar that shoot up a gamma ray, and that gamma ray pass through many millions of years, and now enter into the solar system and enter towards the Earth, and it will hit the upper atmosphere. So this gamma ray will hit the upper atmosphere, and the gamma ray will knock the oxygen and nitrogen molecule in the upper atmosphere and kick out some of the charged particles. So you can kick out a proton from the oxygen nucleus, or you can kick out electron. Let's say kick out electron, and the energy of the gamma ray is very, 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 very great. So the electron kick out is traveling very fast. The electron that is kicked out is traveling in the air faster than the speed of light in the air. How can? I thought nothing can travel faster than the speed of light. No, you can. For example, you have, let's say you talk about water. Water, the refractive index is a certain, say 1.3, all right? Refractive index N is 1.3. So what is the speed of light in water will be C divided by N, all right? C, the speed of light in a vacuum, N is 1.3. So in other words, the speed of light in the water is less than the speed of light in the vacuum. So now what happens is that the speed of light, all right, in this what they call air has a refractive index slightly more than 1. So when the electrons kick out, the electrons are moving at a speed faster than the speed of light in the air, and it will give up the famous Cherenkov radiation. Remember, you go to some of the so-called light water reactor, they produce the power in the world. So from the glow in the water, what color? Blue color. So the blue color is the Cherenkov radiation. The famous Russian discovery, Pavel Cherenkov, 1958, won Nobel Prize, but discovery in 1934. All right. So what happened is they put the bottle of water next to the radio source. Hey, why you got blue color one? It's Cherenkov radiation. That means the charged particle given off by the radiative particle enter into the water. They travel in the water faster than the speed of light in the water, and give us Cherenkov radiation, and keep on giving. So he won Nobel Prize. And the very interesting, 1934 discovered, but I think about 20 years earlier, Madame Curie in Paris, she also saw the phenomena. Water next to the radiative source is blue, but she didn't investigate. Otherwise, she would have won another Nobel Prize. Remember, Madame Curie won Nobel Prize in radioactivity. She would have got more Nobel Prize, she didn't know. So 1934, Pavel Cherenkov discovered, and then 1958 got Nobel Prize. So this is this. So you have this gamma ray from outer space hit those molecules in the upper atmosphere and kick up those charged particles, and those charged will travel faster than the speed of light in the air and give up the flashes of light. So all this will see the flashes of light and they detect. And by counting, by having a kind of 3 of them, they can find out in which direction they come out and so on. So basically, this is studying the cosmic ray. So this is a funny kind of telescope. All right. So it is Magic. So Magic is, I think, run by American, what they call American. No, I think by the European group. Okay, in Canary Islands. All right. So the next one, this is the old object, but this is a new picture. Very nice. Okay. Hey, no, sorry. Okay, this one is 15th of July 2020, few days ago. All right. Comet NEOWISE. This is our Austrian photographer, Philip Salgeber. All right. It's taken over the Swiss Alps, but look, Cinca Sui. It doesn't mean that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 comet. No, there's only one comet. So at one time or that night, they took the comet here, another time is here. So in that night, or over 1 week, at the margins of day and night. So that means he took in a series of different days, maybe over 10 days. All right. So you see the comet over 10 days, and below is the what they call town or village in the Swiss Alps in the valley. So very nice, very nice. So this is our Comet NEOWISE. And then another thing is, you look like, how don't you find that? How come why Comet NEOWISE is pointing vertically up on the horizon? Because this is in Austria, 40 degrees north. In Malaysia, you will never see the comet pointing. This is the horizon, and it's pointing perpendicular. No, in Malaysia, if this is the horizon, the comet will point like that at a very high inclination. I mean, like going to fall down like that. So by looking at the picture, where this angle is pointing, you can estimate which latitude is this picture taken. So this is taken at 40 degrees north. In Malaysia, it will be like this lah. It will be at an angle. All right, like this. If you go to, let's say, Australia, in Malaysia, like that. In Australia, in the south, we're pointing the other direction. By looking at the angle or inclination of comet, you know which part in the world is taken, the latitude. All right. So now, summer got a lot. This is 21st of July. All right. This is a new picture taken of an old object. This was taken by Hubble many years ago. All right. So this is our famous butterfly nebula, taken by Hubble, but processed by this. Can you imagine? Judy Smith is an amateur image processor. No? So there are people who process it, but they call themselves amateur. Maybe they are paid for it lah. This American woman, amateur image processing person. So this is it. So this is a butterfly nebula. All right, taken by Hubble Space Telescope, invisible and ultraviolet. But look at it, so beautiful. So when they took it many years ago in the 1990s by Hubble, later on they took also you can also amateur take like this is a good example of what's called a bipolar planetary nebula. So a bipolar, why like that? Okay, basically they said that the red here is because of the iron. Remember the iron. So basically it's like this. This is a binary star system. A binary star is two stars or different stars orbiting around each other, and one of the star will die. And if this is a single star, a Lone Ranger star, if a Lone Ranger star will die, it will blow up. So the bubble will be spherical, expanding. But because you have a star there, A, and a star B, the star B died, it blew up, the star B blew up. So because of the star A is blocking the star B, you have two lobes coming out, bipolar, like two ears. One is your left ear or right ear. So right in the center, you have a binary star system orbiting around each other. One of them died, and you have the bipolar planetary nebula. And you look, wow, so much detail taken by Hubble. All right. So I think just to look at this picture, you can learn so much of the astrophysics. Very nice. All right. So this is butterfly nebula. All right. NGC 6302. Okay. So the whole length of this bipolar nebula is 3 light years. And then you have another one, Comet NEOWISE at the nebula. Okay, this is not much. This is taken by Jarek Osiwa, another Polish astronomer from Poland. All right, it's taken from Poland. Very nice. This is a country scene. It's a very normal scene. All right, and on here is the comet, the ion tail, which is moving very fast. and the dust tail, which is very small. So the ion tail is charged particle, and the ion tail is affected by the magnetic field of the sun, and the dust tail is many different types of dust of different sizes, and they scatter off white light. And here is our California nebula. Very nice. All right. So I'm very sure in some places in Malaysia you can see from here. All right. And then this one is of course 19th of July 2020. All right. Of course, remember America sent minutes ago the LRO, Lunar Reconnaissance Orbiter. It orbit the moon, took a lot of data. All right. So this one is a video of the moon. You can see the side facing the Earth and also the other side. So most people will say front side facing the Earth and the far side or the dark side. Dark side is wrong because the dark side, the far side, sometimes dark, sometimes black. Or sometimes say the front side and the back side. All right. So now we play it. So this is on the right is actually the front side. All right. But you play. Okay. Front side facing the Earth. This is the far side. The far side has more craters and mountains. Very few seas only on the far side. Far side. Moon, where you have the Chang'e Falls there. And then this is the near side. Got a lot of seas and a lot of mountains. So if you want to explain how the moon was formed, you must be able to explain why the near side got a lot of seas and mountains, but the far side got only mountains. So you must be able to explain it. All right. So this is taken by the Lunar Reconnaissance Orbiter, which is still orbiting the moon. All right. So now you have this one is, I like this one, 16th of July. Okay. Comet NEOWISE again. Petr Horálek. All right. It's taken from the Czech Republic. One amateur astronomer from the Czech Republic. So many amateur astronomers, very nice. All right. So I find here in this picture, I don't know whether how many of you have been to small European villages. So we have seen some of the European villages in this France and other places, like we went to Romania last year. You see the countryside scene, the small village, very beautiful, and on top of it you have NEOWISE. And if this is NEOWISE, which this was taken when? This was taken in July 16. So this was not the closest approach. So this was taken in the morning sky. After July the 23rd, it's taken in the west, in the western sky. So this is taken in the morning in the eastern sky. All right. And this is approaching the sun, approaching the sun, since this is the ion tail here. So that means the actual comet must be moving in this direction, closer to the sun. All right. This way, the comet is moving. So now we find also a lot more. Okay, this is very nice. I'm sure you all should know. No need to say lah. Okay, Comet NEOWISE. I visited this place before. It's a town called Salisbury in Wiltshire, South England, Stonehenge, and the comet. Very nice. All right. Well, we all know that Stonehenge is kind of a big astronomical, what they call a monument that align those rocks, pointing to certain parts of the sky. All right, by the famous people of England called the Druids, Druids. The Druids are the original inhabitants of England, even before the Gauls and the Anglo-Saxons, but they all died out already. So the Druids built this very tall. I was there before. If you stand there, you know how you are. Like you're only so tall. I think here also got 2 or 3 story high. So this is the Stonehenge with NEOWISE. All right. So make it bigger. Another one. So we don't go to NEOWISE, always NEOWISE. This one. Okay. Now remember this one. Some years ago, the ESA, European Space Agency, launched their famous Rosetta mission. Rosetta mission is launched by the European Space Agency from Kourou. Where's Kourou? French Guiana, South America. Remember, the French got a colony still there called French Guiana, and they have one of the largest spaceport in the world, but only launched unmanned space probe. All right, Kourou, and they launched the Rosetta spacecraft. And remember, the Rosetta actually orbit around this comet for some time. And you know what happened? The Rosetta actually landed on this comet. But this is not a comet. This is the comet nucleus. The comet nucleus is what? Dirty snowball model, frozen ice, rock, carbon dioxide soot, and so on. But what is beautiful is, yeah, you see, it got smoke, not smoke. The sunlight, the sun's energy will vaporize those volatile materials frozen there, become vapor, and this later on will expand and form the coma of the comet. And later on, the solar wind keep on blowing onto the coma, expanding, will create the tail, the ion tail and the dust tail. All right. And this comet, of course, discovered by Russian. All right. This one we have given talk before, and very interesting name. Okay. The comet name is our Comet 67P. P means superior comet. Churyumov-Gerasimenko. So this is found by two Russian astronomers, all right, named after them, and the European spacecraft actually orbited and landed on it. And you saw some picture. They landed on. So this is a 4.5 kilometer wide nucleus, 2 kilometer, and there's a small neck there. And I think the Rosetta actually landed somewhere at the neck. This comet is not direction in the distance from the moon, you know. This is very far away from the Earth, you know. All right. And remember, why do they call it the Rosetta? You should know. So the name is called the Rosetta mission, Rosetta spacecraft, because remember, the Europeans have found the ancient Egyptian writing in the pyramid. They couldn't decipher, could not decode it until one French linguist, what they call Champollion, was able to find on a stone in Egypt. It's called the Al-Rashid stone. And the Al-Rashid stone, you have both Greek letters and the ancient Egyptian hieroglyph. All right. And because of that stone, Al-Rashid stone, he was able to decipher the ancient Egyptian writing. But the Australia, you know lah, Al-Rashid, they go and corrupt the name, so Rosetta lah. So the Rosetta stone is the stone that Champollion in France, and later on, all the people who study the Egyptian civilization was able to read the ancient Egyptian writing from the Rosetta stone. All right. And remember, the people who study the ancient Egyptian civilization are called the Egyptologists. So this is called Egyptology. All right. The Rosetta stone. Sorry, I go up from astronomy from time to time. All right. So now you go to some more. Oh, this is the tails of Comet NEOWISE. So now remember, I really like this. So before I show our this one, the picture from the amateur Chinese astronomer photographer, I like this one better. But now the Chinese one is better because the ion tail and the dust tail. But this is taken by what? By our famous Miroslav Druckmüller from Czech Republic. Remember, there's an amateur astronomer, he's a professor, Miroslav Druckmüller. All the total solar eclipse, he processed the picture. Wow, very nice, you know. The total solar eclipse processed by Miroslav Druckmüller. So this is his picture, processed picture, and this is taken from Czech Republic, and then he processed it. You can see the straight tail and the curved tail. So I find that what is nice about this comet is not just the scientific aspect, but it is very, to me, very artistic, very nice, right? By Miroslav Druckmüller, Comet NEOWISE, when it was still approaching the sun, taken in the morning sky. So now we continue. Okay, this one, I think some of you would have seen before. I saw it when it came from the International Space Station. All right. So this is our current expedition, ISS number 63, which we have, I think, about 6 people up there, 3 cosmonauts and 3 astronauts. All right. And there you see the NEOWISE rising. It's so bright you can see. And this is a star. And I think this is one of the small module attached to this is a Japanese module attached to the Kibo module. All right. Kibo is the bigger one. And attached to this is another Japanese module. And here is the Earth. And this is maybe the morning sky. All right. So actually now the ISS is approaching towards the east. And you can see the NEOWISE rising. And on top here is another part of the what they call ISS, International Space Station. Very nice. Okay. So now we continue. So half the pictures for July are from what they call this NEOWISE. Okay. This is very nice. By one what they call Emanuele Pauli. This is I think Italian amateur astronomer. All right. and it's taken from this. And what is nice is, look here, you have here the comet taken in the morning sky in the east, and you have here the noctilucent cloud. Remember, noctilucent cloud, I've never seen any Malaysian taking, but it can take in Malaysia. So basically, like this, noctilucent clouds are very high up, about the highest part of the sky before you reach outer space. Remember, outer space is 100 kilometers from the Earth's surface and above. Just below the outer space, you have the higher, very high up there. So you have those meteors or volcanic dust. They blown out into the upper atmosphere of the meteors coming into the Earth. They burn. So this tiny dust particle in the upper atmosphere will form the centers of nucleation for what? For ice. Tiny ice particle. And these are the noctilucent cloud high in the atmosphere with the comet. Very nice, huh? Emanuele Pauli, right? From this Italian, what they call amateur astronomer. Continue. This is very rare. So this is the one I want to ask Chungchat CK to do. So so this is our 8th of July 2020 by Andrea Alessandrini, another Italian astrophotographer. I'll read for you what it is. So the title is Mercury Sodium Tail. Remember, I think in the early 2000s, Americans have sent in the messenger, what they call robotic spacecraft to orbit around Mercury, and they detected sodium in the space close to Mercury. So this Italian amateur astronomer Andrea Alessandrini in Italy did a long exposure of the Mercury, but he has a filter in his camera to allow only the spectrum lines of sodium. And he observed a tail in Mercury. This is not a comet. This is Mercury with a tail, sodium tail. So maybe if we can get the correct filter for CK, do it lah. Very nice. This is a short starter here and there. So this is a this is a sodium tail of Mercury, right? So Mercury's tail was first discovered in 2001, and later on the messenger aircraft about 10 years ago also detected it. Now this guy, he took a picture with a filter on top of his camera, and he took Mercury with a sodium tail. Very nice. You see, this is the diameter of Mercury. So I see at least about 20 diameter. So the sodium tail is 20 times the diameter of Mercury. That means what? That means most likely, I didn't check, most likely, remember, Mercury don't have a thick atmosphere. It's just like the moon. So the sun's energy full blast on the Mercury surface and will kick out the sodium atom from the surface of Mercury. And this sodium atom kick out from the surface of Mercury will form an atmosphere of thin atmosphere of sodium atoms around the Mercury. And at the same time, why you form the tail? Sunlight. So the sun is below here, just like a comet. The sunlight will blow away the sodium atmosphere of Mercury to form the sodium tail of Mercury. Right? So this is our sodium tail of Mercury. TAIL. Very interesting, huh? So maybe you can ask Chungket to take, if possible, the sodium tail of Mercury. Very interesting. All right. So now we continue. A lot of those NEOWISE. Let's go to a non-NEOWISE one. 6th of July. 6th of July. You know it before. Of course, you have seen CK doing this, Chungket. So basically, it's M43 dust gas stars in the Orion Nebula. Of course, taken by Hubble, but you see, I don't know why nowadays, a lot of the pictures taken by big telescope on the Earth and in space, but the people processing it are all amateurs. So Brian Goff, amateur American astrophotographer, all right, he processed it, all right. So one of the reasons I can understand why Brian Goff, amateur astronomer, processed, why this Brian Goff, what, a lot of stamina, a lot of patience. The powerful astronomer working in NASA, ESA, don't have time to do it. But amateur, a lot of time, a lot of dedication. They spend a lot of time to process them. That's why this is our M43. Part of this is a great Orion Nebula. You see the details, right? So again, here I can see, remember, nebulae are of three types: emission, absorption, and reflection. So here you have a star given light, and it energizes and excites the atoms in the space there. What do you mean by energize? That means the UV light from the star emitted hit some of the atoms, say hydrogen atom, helium atom, whatever, nitrogen atom. So the electrons are excited from a lower level to a higher level. And then they will drop into a lower level and emit the light. So what is this basically? This is what? Fluorescence lah. So basically, this whole initial nebula is a gigantic fluorescent tube, fluorescent bulb. But it gives out different color because depending on the element, the higher level electron shell to drop to lower level can have different color. All right. This is our absorption nebula. That means here a lot of dust in between the star. This can be many light years. And behind there, there's a bright star. But the bright starlight is blocked by a lot of dust here. So it blocks the light from behind. So you see absorption nebula. I said the reflection. I don't see a reflection. Sometimes you can see a reflection, but there's no reflection nebula here. So you have emission nebula, you have absorption nebula. And of course, you look at the detail. Wow, like artist painting, so fine detail. So again, we know Great Orange Nebula N42, N42 are what? They're called what? Tadika Bintang, stellar nursery. So Hubble have seen inside here in the Great Orange Nebula N42, 43, hundreds of thousands of what? Protoplanetary disks. That means those clouds of gas and dust collapsing, and wait now long enough. Long enough in astronomy doesn't mean one day, doesn't mean 10 days, could mean tens of millions of years. Then, wow, a star is being born. So they have found inside the Great Orange Nebula, Hubble Space Telescope, few 100,000 protoplanetary disks. So this is where many stars will be born with exoplanet, with aliens in future. Right here, this is in Orion. This is in the sort of Orion. All right, M42 with the dust, gas, and the stars. All right, Orion Nebula. So we continue for July. Okay, this one is the old information, but it put on the 5th of July. All right. Okay. The hexagon of Saturn, the northern pole of Saturn. Of course, this is taken by the Cassini division by NASA. Remember, Cassini no more. Where's Cassini? Cassini now is buried in the clouds of Saturn. Remember, Cassini orbited the Saturn many years, and not to contaminate the moons of Cassini of the Saturn, NASA deorbited and crashed and fell into the atmosphere. It's now in the center of Saturn. So what it did is Cassini took this picture of this not polar region of Saturn, and you see what? The famous hexagon. And you can put inside this hexagon 4 Earths. So now until today they want to understand how the hexagon formed, not 100%. But I saw one of the paper, this is it University of Oxford? They did this simulation, that if you have this type of rotating fluid, where between one of the inner part and outer part flowing with different density and so on, it will form a hexagon. So this thing is rotating at the North Pole of Saturn. So this is a kind of a mysterious object. So I remember when this was first found published by NASA many years ago, everybody was scared. I was scared. What? Alien civilization controlling Saturn. Where got a natural object have a 6-sided hexagon so accurate? So it must be formed by what? Intelligent being lah. But now no, it can be explained by natural process. What? Not fully understood. And what is this thing here? The blue one, the rings of Saturn lah. All right, taken by Cassini. And of course, remember one of the important mission objective of Cassini, they dropped out from Cassini the famous Huygens probe, the unmanned space probe that parachuted into Titan, the big moon of Titan, and sniffed out the air and took a picture and found got methane lakes, methane ice, a lot of data. All right, but very unlikely to have life on Titan because Saturn is very cold, minus 200 degrees Celsius. So Titan also minus 200 degrees Celsius. But anyway, got organic material on Titan. And another one you can try, Lighthawk, is amateur astronomers have looked at Titan with their own telescope on the Earth in Europe and passed the light from Titan through the telescope through a spectroscope and split up the light into the spectrum. And they have detected organic molecules in the atmosphere of Titan from the Earth with the amateur telescope with a spectrogram. The only thing is you need a spectrogram. So some spectrograph need not be expensive, right? So you can detect organic molecules on the moon of the planet or even on a comet. Many of the amateur astronomers will look at the comet NEOWISE, the light from the comet NEOWISE. They will study what is the element on the dust tail of this comet NEOWISE or the straight blue tail of the comet NEOWISE. Okay, so now we still on July. Bigger, sorry. You are going to end now. So July, okay, this one is July the 4th. This is nice. Ho. This is by Stefan Better, I think this is another French amateur astronomer taken in the Vosges mountain in France. So basically it's like this. Hey, what's on top there? What is this? Alien landing on the Earth? No. These are the famous sprite lah. Somewhere in France, mountain, the Earth cloud, the stars, the sprite. This is not the minimum sprite. Huh? Remember many years ago, SPRITE, the gaseous dream called sprite. No, this is the lightning in the upper atmosphere. Just to let you know, I think this USM lecturer, I know him very well, has stopped this research. Dr. Wong Chao Jing of the School of Physics, before retired, he actually engaged the group of people from Taiwan. So the people of Taiwan were studying sprite, So that means you have camera that point at the upper atmosphere. This is close to the space, very high up. This is not from here to here 10 kilometers. No, from here to here maybe 30, 40, 50, 80 kilometers from the Earth's surface. So you have special type of lightning can create lightning strike. So all these are lightning. So this is what electrical discharges in the upper atmosphere. But here also they say that there's also lightning, but this lightning is our normal lightning above the Earth's surface. But these are the lightning in the upper atmosphere close to space. So can see, in fact, the International Space Station people look down on the Earth, also can see sprite from space. So these are the sprite seen in France. So next time, if you go to take some picture in Langkawi or anywhere in Malaysia, in the dust time, you see something, don't go, wrong lah, you go and throw away this picture. No, this could be a real data. These are the sprite, the red sprite, SPRITES, right? Electrical discharges in the upper atmosphere. How often do sprite occur? All the time. Every day they occur all over the world. How come you say, how come I don't see it? Because you're not observant enough. There are people who can see sprite with their own naked eye one, right? So next time if you take picture, be aware that see whether you have captured sprite. But this is a sprite taken from France by this what they call Stefan Better, and this in the mesosphere. Remember, the mesosphere is a part of the atmosphere which is very close to space, very close to 100 kilometers. So in the upper atmosphere, right? Sprite, right? Above France. Not the drink, the electrical discharge. So we continue for July. Okay, we go to July 2nd. Okay, this one very nice. Okay, this is taken by Christine Richer. I think this is by an American woman astrophotographer. No. Christine Richer is actually a landscape photographer. You see, many of the astrophotographs got Milky Way are not taken by astrophotographer. No, they are the normal landscape. They take the sea, they take the clouds, they take the sailing ship. But at the same time, at night, if they got the Milky Way, they put in. So this is a normal landscape astrophotographer. Milky Way, Jupiter, reflection of Jupiter, reflection on the water with the star tail and the apple tree. All right, the galaxy, Milky Way, the planet Jupiter, and the apple tree. So very nice, simple idea. All right. So I tell you what, why not some of you go to somewhere in Malaysia, Milky Way and then coconut tree and right here durian tree, and then you have a lake here. Send it to airport. Very rare, right? Something that is particular, unique to Malaysia. This is of course apple tree. You go to Europe, America, Japan, everywhere got apple tree. But you put a durian tree, a coconut tree, especially, that will be great. So you next time you go anywhere, got the durian tree, coconut tree, please take Milky Way, believe. All right. I remember Achap, he took a lot of pictures of the Milky Way with the coconut tree, but unfortunately a lot of light. All right. So that's it. We go to the last picture, which is our July the 3rd. July the 1st, you have been already. You go July the 3rd. Okay. I make the font big. Okay. 3rd of July 2020. All right. Our Linz Dark Nebula. Era Jerahian. His name doesn't sound like Marcellus. I didn't check from this country. So this is a Dark Nebula, LDN, Linz 1251. And then this is taken, okay, from which country? They didn't check. So this is our Cepheus constellation. Where Cepheus constellation means the king of Ethiopia. All right. And of course, this is the Linz dark region. Of course, we know lah. Dark absorption nebula. Block off the light from behind. And there's a star here, and a bit of emission nebula here, and a bit of gaseous nebulosity. So so basically the nebulosity or the dark cloud is what? They are the so-called, whenever you see a nebula, straight away the next thing you must think in your mind is molecular clouds. What do you mean by molecular cloud? In the molecular cloud, got molecules lah. What are molecules? Many, including many organic molecules. So you can see in the textbook now, let's say you look at the Great Orion Nebula, they list out in the Great Orion Nebula, there are maybe up to 100 organic molecules. So many of them are organic molecules, but ethane, okay, CH4, methane, C2H6, all right, ethanol, which is pure alcohol, methanol, acetone, benzene. So all types of complicated molecules, even amino acids, they are found in it. So how do they know? Many ways. If you have this bright star, they energize it, they'll give off the light. Then the molecular give off light. So they see the light. So what is the light? The light is the transition between the electrons in the molecule. Will give off the light. From the signature of the spectrum, they know it's what molecule. But sometimes also, for those which are cooler gas, for example, here it's not hot, this hot gas is cooler. So what you give off? Infrared. So infrared is like that. Infrared is the molecule, say alcohol molecule is rotating, right? So when you have a molecule rotating in space, it will give off radio wave. And because it's a kind of quantum mechanical phenomenon, so the radio wave is also spectral line of the spectrum line is in the radio wave region, not a continuous wavelength, but certain discrete line in the radio wave rotation of the molecule. Or sometimes you have a warmer infrared. Let's say here you have an infrared cloud. Or infrared is what? The molecule is vibrating. Imagine you have O2, oxygen. One atom of oxygen next to it, and the atom combined with the covalent bond. So the two oxygen atoms are closer and further apart, they're vibrating. So when by vibrating, what they give out? Infrared light low. So by studying the radio wave, they study that the molecules are rotating. By studying infrared, you know the molecules are vibrating. They study the visible light, the electronic transition level in the molecules. So by studying all wavelengths, they can know so much about those molecules in the molecular clouds. All right. So next time, maybe in one of the next one in August, I'll list out what are the organic molecules they can detect in space. All right. So what does this say? This is basically a gigantic chemistry experiment. So remember, the old term is called what? Cosmochemistry. So you put here so many organic molecule and so on. So with gravity, so you simulate it, you find that so many stars will be born, and then later on planets will be born and so on. I remember when I gave my lecture many years ago, I said the scientists, imagine, the scientists have found here that there's a quarter light year, a cubic, 1 cubic light year of what they call ethanol, which is pure alcohol here, but it's in the form of what they call molecule in space. But because the space is 1 cubic light year, so I told them, you estimate how much? Oh, they calculated, the student, 1 trillion swimming pool of pure alcohol there. Wow, 1 trillion swimming pool of alcohol there. And another one, you check the girl, they use the lipstick, isn't it? They apply the lipstick on the mouth, the red, the mark there. the lipstick has a certain organic molecule. So I told the other student at night, in last time we observed behind DKU in USM. So here, there is another, let's say 2 cubic light years of that organic molecule. And here also like 10 trillion, 10 trillion, what you call swimming pool of your lipstick there. So here you have a lot of organic molecules. So that's why they say, maybe that's why life is all over the universe, because they have found organic molecule, the organic molecules in all of space. Remember, they have found hydrogen and all the atoms, elements, 120 elements in the periodic table on the Earth, in the solar system, by studying the spectrum of the stars and so on, and also nature as well as Earth. And similarly, by using all the telescope, radio, optical, they have found all the elements right to the edge of the universe. So they have not found on Mars a certain element that doesn't appear on the Earth. Wrong. So every element on the Earth is found similarly in the whole universe. Very unlikely to go to land on one of the planet somewhere in the Milky Way. You find that all the elements are different. Cannot be. You should be like the same as only that the combination of elements are different now. So they give different compounds in those planets, right? So all elements on the Earth are found throughout the universe. So that's why we are very confident that if you analyze the hydrogen spectrum of the Earth and you analyze the hydrogen spectrum from the edge of the universe, they're exactly the same. So what you study on the Earth, any molecule in the universe is exactly the same. All right. So I think it's about that's about it today for July. Yeah? Okay, this for July. So any comment, Michael and Lai Hong, any comment by the listener? Question? Any comment? Lai Hong, Kim Chong, any comment? Lai Hong, any comment? Kim Chong, you recorded everything already, yeah? Okay, yeah. So any comment in the YouTube? So okay lah, right? So okay, so I will end. Okay. So again, we like to thank our Michael Teo for arranging everything. All right. So this is it. So we continue for July. We start again by the part 2 of the jewels of APOD and the continuation of the APOD pictures for August. All right. So thank you very much, everyone. Good night. Thanks to Michael and Lai Hawk. Bye bye.